Okay, we are on Chapter 11, Section 2, Acceleration. So let's look at key ideas in the section here. What changes when an object accelerates? How do you calculate the acceleration of an object moving in a straight line? And how can a graph be used to find acceleration? Let's bypass the bell ringer here, so let's get it started. What changes when an object accelerates? When an object undergoes acceleration, its velocity changes. We talked about velocity in the last section, about what velocity is. Velocity is the speed with direction. So if the speed is changing or if the direction is changing, either one of those, then the object's is under what's called acceleration. So acceleration defined here is the rate at which velocity changes over time. And you see here if an object accelerates, if its speed, direction, or both of those change. So it could be just its speed changing, it could be just its direction changing, or both could change. Any one of those three things is what constitutes acceleration. So acceleration can be a change in speed, an increase or decrease in speed. You can be a change in direction. So like a motorcyclist who rides around the inside of a large barrel. If you've seen those big cages where the motorcyclist rides around inside the cage, up and down and all around in like a circus atmosphere. Excuse me. Even though the motorcycle is going at a certain speed, its direction is changing, so it is accelerating. Riding on a Ferris wheel, again, because your direction is changing, not just your speed. And acceleration that occurs in circular motion, that's called centripetal acceleration. That's always directed inward toward the center of the circle. So how do you calculate acceleration of an object moving in a straight line? So average acceleration over a given time interval can be calculated by dividing the change in the object's velocity by the time in which that change occurred. So you can see here the formula. Average acceleration is the final velocity minus the initial velocity divided by time. Excuse me. And that final velocity, remember, that's whatever the velocity is at the end. Initial just means whatever the velocity is at the beginning. In shorthand or symbol form, A is equal to VF minus VI over T. Or actually in this little box right there next to V, that should be a triangle symbol, which is delta V, which means change in velocity. So acceleration is the rate at which velocity changes. In this book for straight line motion, a positive acceleration means the velocity or speed's increasing, so it's speeding up. Negative acceleration means it's slowing down, basically. And the SI units of acceleration are meters per second, or we commonly write that as meters per second squared here. Excuse me. So let's watch a little visual concept here.
An object changing speed is accelerating. The equation for acceleration is the change in velocity divided by the time required for the change. Acceleration can be calculated by knowing the initial and final velocities and the initial and final times. Like velocity, acceleration must also include direction. The velocity of this cyclist is increasing by 1 meter per second south each second. His acceleration is expressed as 1 meter per second squared south. If an object slows down and is traveling in a positive direction, the change in velocity is a negative value, so its acceleration will also be a negative value. If an object has a negative velocity, such as when the bicyclist heads the opposite direction and is accelerating in that direction, the acceleration will also be negative, even though the bicycle is speeding up. If there is no change in an object's velocity, its velocity is constant and its acceleration is zero. If an object has constant speed but changes direction, then its velocity is changing and it is accelerating.
Alright, so let's continue here. So acceleration, mass scales. A flower pot falls off a second-story windowsill. Flower pot starts from rest and then hits the sidewalk 1.5 seconds later with a velocity of 14.7 meters per second. So find the average acceleration of the flower pot. So first we got to list the givens and unknown values here, and what information the problem gives us and what we don't know or need to find out. So we're given that the time was 1.5 seconds. The initial velocity was 0 because it starts from rest there, which means it's starting from 0 meters per second. And then its final velocity, just as it impacts the ground, is 14.7 meters per second. And what is unknown is the acceleration. That's what we've got to find. So we write the equation here. Acceleration is final velocity minus initial velocity over time. We insert what we know about those givens into the equation. So the final velocity was 14.7, the initial was 0, so it's 14.7 minus 0 divided by 1.5 seconds. When you divide those two out, it gives you 9.8 meters per second squared, and direction is down. That's the way it was accelerating. So how do you graph how can you use a graph to find acceleration? On a speed versus time graph, which you can see here, the slope of the line on that's equal to the acceleration. Just like on a distance time graph, the slope of the line was velocity there. In this case, you have, if you do rise over run, speed in meters per second divided by seconds, meters per second is the acceleration. So the slope of the line on a speed versus time graph is equal to acceleration. So acceleration can also be seen on a distance time graph. As you see here on a distance time graph, right here in the bottom portion there, it has a curve to it. On a distance time graph, if there's any curve whatsoever, that means some kind of acceleration. And remember, acceleration could also be negative, which means it's the object slowing down. So the graph of the distance time graph is not a straight line, so the velocity is not constant, which means there is an acceleration. And the curved line indicates that it is under acceleration. So let's again watch this. Watch another video here about velocity time graphs.
Acceleration measures the rate of change in velocity. You can find the average acceleration of an object if you measure its velocity at 2 moments in time and divide the change in velocity by the time required to make the change. You can also determine the acceleration of an object from a velocity versus time graph of its motion. Consider an object whose motion is represented by this graph. Let's find the average acceleration for the time interval from 4 seconds to 10 seconds. Average acceleration is simply the change in velocity divided by the time of travel. In other words, the average acceleration equals the slope of a velocity versus time graph over a time interval. The acceleration at any moment, called the instantaneous acceleration, can be found by shrinking the time interval. As the time interval becomes infinitesimal in size, the value of the average acceleration approaches the instantaneous acceleration. The instantaneous acceleration at a particular moment in time is the slope of a line tangent to the velocity time graph at that time.
Alright, so let's move on here. Graphing skills. So we got a bus traveling on a straight road at 20 meters per second. Uniformly slows to a stop over 20 seconds. Bus remains stopped for 20 seconds, then accelerates at a rate of 1.5 meters per second squared for 10 seconds. Then continues at a constant speed. So graph the speed versus time for 60 seconds. What's the bus's final speed? So we determine the x-axis and the y-axis of our graph. Generally, the x-axis will always indicate time. That's our independent variable, all measured in seconds, and the y-axis will indicate the speed, v measured in meters per second. That's the dependent variable. So starting from the origin, graph each section of the motion. So draw and connect first 2 points from t equals 0 seconds to 20 seconds. The van went from bus went from 20 meters per second to 0. So we start here at, he was going at an initial velocity of 20, and by the time he got to 20 seconds, he had slowed down at a constant acceleration to 0, He stayed still for a little bit, for 20 seconds. So draw a horizontal line from t equals 20 to t equals 40 because he was still. At that point, it didn't go anywhere. And then at 40 seconds, his velocity was 0, and you draw a line with a slope of 1.5 meters per second. So you draw it with 1.5 meters per second. So in 10 seconds, he's gone up to 15 meters per second. And then he was at constant velocity again. So draw a horizontal line from t equals 50 seconds to t equals 60 seconds at 15 meters per second. So this horizontal line just means a constant velocity of 15 meters per second all during that time. So read the graph to find the final speed at t equals 60. The speed was 15 meters per second, so that is the